I'm David Long from Brigham Young University. Along with my co-authors, Rajat Bindlish, Giovanni Diamica, Jeff Pietmeyer, and Mark Bailey, I'd like to talk to you about the Global L-band Observatory for Water Cycle Studies, or GLOWS. SMOS, Aquarius, and SMAP have all clearly demonstrated the ability to measure soil, moisture, and ocean sea surface salinity from space. Other applications of the L-band data were demonstrated for sea ice observation and measuring of ocean surface winds. Unfortunately, there are no plans for a future U.S. L-band mission. This is primarily due to the cost of the large antennas required for L-band observations. To address the need for a continuity mission, or perhaps a mission that can be used that is complementary to the GLOWS mission, we have proposed the GLOWS program to the NASA Instrument Incubator Program. As part of this program, we're going to demonstrate the use of a rotating lens antenna that we can operate on a small spacecraft. The goal of this mission is to design an antenna, a lens antenna, that we transmit the signal down through the antenna. The antenna then tilts it off to the side, and as we rotate the lens antenna or about the nadir axis, we can provide a scan much like an offset fed antenna that was used by SMAP. Here's a comparison of the SMAP and the GLOWS missions. The flat structure of the lens antenna simplifies the rotation because it now occurs in a very balanced way, and it's also much lighter weight than a rotating parabolic mesh antenna. This allows us to fly the antenna system and the entire instrument system on a much smaller spacecraft, which makes it less expensive. The goal of the GLOWS mission is to basically be a follow-on for SMAP. It'll include both an active radar channel and a passive radiometer set of channels. We'll provide multipolarizations for both the active and passive channels to make measurements of the brightness temperature and the surface backscatter over a very wide swath. The key goals in our study for the NASA IIP is to understand the radiometric efficiency of the lens antenna. That is, we need to know the ohmic losses. Can we achieve the desired antenna pattern with the efficiency? Can we understand how to best measure and correct for any temperature effects on the lens itself? We have to be able to demonstrate that we can, in fact, deploy the lens antenna correctly and spin it, and that the gain and the spin are stable over long term. We've made significant progress on this, and I'd like to show you a video of the actual deployment of a membrane antenna. This is prepared by MMA Design, which is one of the partners in our development. In this video, we can see the struts that deploy the membrane antenna. This is a somewhat smaller system, but it's comparable in this to demonstrate a zero-G deployment in space. The weights that you can see moving are there to help offset the weight, so it is more like a zero-G simulation. This is very much like the design we'll be doing. This is providing an offset fed to be used as a reflect array antenna, whereas we'll be using a lens antenna. In summary, the GLOWS mission will be a follow-on to SMAP, providing both active and passive observations. It will be designed to measure soil moisture, ocean surface salinity, ocean surface winds, sea ice, and vegetation biomass. It can be used as a continuity mission between SMAP and SIMR, or as a complementary mission in a complementary orbit to the SIMR, providing both L-band observations that are passive and active. Thank you.